So now it's time for the second talk this morning. So we have Yannis Voet from EPFL in Lausanne, who is going to speak today about mass being in explicit dynamics. So the floor is yours.
Thank you very much. So indeed we'll be talking about mass in explicit dynamics, and more specifically in the context of isogeometric discretizations. So I'll start with a brief introduction, of course, introducing what mass mapping is and why it is useful. And then we move on to some preliminaries, meaning on notation, and just some general knowledge necessary for the rest of the talk. And then we'll be analyzing actually mass mapping and then generalizing to other non-diagonal structures, more complex structures. And finally, I'll be mentioning some ongoing research and also some future work. So most of the results are actually, the results I'll be presenting here are just a sample of what will be contained hopefully in an upcoming paper, which I'm preparing with my supervisors, Arenzano and Arenzano. So the problems we're considering here are problems where mass mapping has been historically used. Time-dependent PDEs from structural dynamics. And those are second order in time because this term here accounts for acceleration. So normally there are material coefficients, but let's ignore those for simplicity. And obviously we know some very simple boundary conditions, but of course we could increase the complexity here. We could also consider different differential operators. Here's the Tiscan Laplace that puts in bilaplacian, for instance, to model plate problems. We could also consider vector PDEs of linear elasticity. Mass mapping is used in quite a large variety of problems. Now, as you probably know, if you want to get an approximate solution of this problem, there's a two-level approximation traditionally used, a spatial approximation and temporal approximation. Now, the spatial approximation, if we use standard Galerkin discretizations, that leads to this semi-discrete problem. We have this mass matrix M, this matrix K here popping out. Now, of course, the properties of these matrices depend on the discretization method you'll be using. And here we'll be using isogeometric analysis. So we've already heard a few talks using this method, and I won't be adding much here. The only thing you should know is that these discretization methods are based on spline basis functions. The same functions that are used in the computer-aided design community, so B-splines or NURBS. And these spline basis functions allow to construct approximate spaces with increased smoothness. And this increased smoothness is actually provably linked to an increased accuracy per degree of freedom. So to get the same error, you only have to consider fewer degrees of freedom in comparison to classical FEM based on Lagrange basis functions. And the interesting property we'll be using from this method is that if you use this isogeometric analysis, the mass matrix is actually a non-negative matrix due to the non-negativity at the spline basis. All right, and then once you're left with this semi-discrete problem, well, there's a whole range of methods you could use, time-stepping methods, to get an approximate solution. And the one we'll be using in this talk are actually explicit methods, which have been traditionally used. Now, why explicit methods? For two main reasons: robustness and accuracy. Robustness, because they are believed to have better conversion properties for highly nonlinear problems, and accuracy, because we're considering problems where the loading is varying quite rapidly, and boundary conditions and so forth. So we anyway have to consider a sufficiently small time step for us to recover physical behavior. So there's no point in using implicit methods because you do not benefit from the unconditional stability of these implicit methods. Now, one explicit method which has been used all over the place is this central difference method. Now we see this is based on computing an approximate solution for the acceleration, velocity, and displacement, and so forth. So it starts out with some initialization, then you have a loop over the number of time steps, or any number of time steps. You get some vector updates and so forth. And at some point, you have to solve a linear system with the mass matrix at each time step. And this is a real bottleneck in these algorithms. Of course, it's not something new. Engineers have been facing this problem since the early days of the finite element method. But there are some additional challenges which arise in isogeometric analysis, which I'd like to highlight here. And the first one is linked to stability. This method being explicit, its time step is constrained to be smaller than a critical time step, otherwise the method blows up. And this critical time step is unfortunately inversely proportional to the square root of the largest eigenvalue of the generalized eigenvalue problem, kx is lambda mx, so it's just shorthand notation to denote this generalized eigenvalue problem, and lambda n is the largest generalized eigenvalue. And this quantity turns out to be completely inaccurate. For maximally smooth B-splines, the entire spectrum converges to the one at the continuous operator, except for a few here at the extreme part of the spectrum, which are completely inaccurate and grossly overestimated. And these are called outliers in the isogeometric community. They arise from maximally smooth discretizations. and they are completely polluting the CFL of our explicit scheme because they rise to the denominator here. So this is our first problem. So we have a lot of linear systems to solve, and each one of these linear systems, unfortunately, is also quite challenging. This has been reportedly the great performance of sparse direct solvers and iterative solvers, and this is in close connection with an exponential growth of the condition number of this mass matrix with the spline order. So it's all in our interest to actually not even solve linear systems with M, but straightforwardly replace in time-stepping scheme the mass matrix M with an approximation M hat. And this may seem quite scary, you know, but it is used all over the place in engineering. And people don't ask too many questions about the accuracy of the solution. It's quite frightening. All right. Now, what are the main methods that have been used to get this approximation? There are three of them, and the first one is the row sum method. Now, these are all heuristics, so you know, I'll just list these few examples, and then we'll be analyzing one of them. So the row sum method is very easy. Just define a diagonal matrix with the ith diagonal entries, the row sum of the entries on the ith row. It's very simple, very easy to implement, straightforward, you know. Second one is called no-approach method, and this is something very specific to traditional classical FEM based on Lagrange basis functions. But what it does is that it chooses a very special quadrature rule such that the quadrature nodes coincide with the finite element nodes. If this property is satisfied, and if you are using Lagrange basis functions, then actually this naturally leads to a diagonal matrix immediately. And the third one is called diagonal scaling method. Now this one just extracts the diagonal of the consistent mass and then scales each one of its entries by some factor here that's cost. All right. So apart from leading to a trivially invertible mass matrix, there are some other claims around mass dumping, and these are linked to an improved stability, namely an increase of the critical time step, and also that it seems to faithfully, at least for lower discretizations, reproduce dynamic behavior. And this is closely linked to the fact that mass lumping, at least numerically, tends to well approximate the low frequency part of the generalized spectrum, and this part is really critical if you want to get a good dynamic behavior. This is the part that enters predominantly in the dynamics of the problem. If you get this part wrong, there's no hope that you'll get a good solution actually. So if you want to understand mass lumping, from a mathematical point of view, you have to kind of tackle these two problems. You have to understand accuracy, showing that actually the eigenvalues for the perturbed problem, the smallest guys, are well approximated, and stability, showing that the largest guy is actually smaller or equal to the one for the unperturbed problem, because since critical time step is inversely proportional to the square root of this guy, if this is satisfied, you'll actually get an increase in the critical time step. Now, of course, there's been some results for these two aspects, but those are quite scattered in the literature and restricted to classical finite element methods for lower discretizations and so forth. What I'll be presenting here is something quite general. So the framework we'll be using here is that M and K are mass and stiffness matrices from isogeometric analysis, are both SPD, symmetric positive definite. This is always the case for M if you're using standard Galerkin. For K, it is usually only positive semi-definite, but this assumption means that actually we'll impose some Dirichlet boundary conditions, and this is fine because anyway, if it's positive semi-definite, this will generate zero eigenvalues, so we can ignore that. M hat will be some kind of approximation of the mass matrix, which we won't be assuming to be diagonal. And just so that you know, I'll be saying general results for general matrices A and B, because my plan is also to reuse these results. Now, just a reminder, if you're solving a generalized eigenvalue problem with A and B SPD, then you can show quite easily that the generalized spectrum is strictly positive. So all eigenvalues are strictly positive. And I'll be denoting this capital letter lambda to denote the spectrums instead of all eigenvalues. And I'll be using the lowercase letter lambda to denote individual eigenvalues, which I'll obviously assume ordered increasingly. So lambda 1 is the smallest, lambda n is the largest. Now, if you want to study the eigenvalues of a perturbed generalized eigenvalue problem, what you're seeking is bounds on the perturbed eigenvalues. And a convenient way is to use this theorem, because what it says is that if you're given a matrix pencil AB, the kth eigenvalue can be bounded from below and from above by eigenvalues dependent on other matrix pencils AC and CB. And this is valid for any SPD matrix C. So if you choose C in a convenient way, you can actually get some very insightful results. Namely, if you use this first inequality up there, and if you choose K and hat to be AB and C to be M, actually if you just rearrange this inequality, you get straightforwardly these bounds, stating that the ratio of perturbed over unperturbed eigenvalues is bounded from below by the smallest eigenvalue of m hat, and from above the largest one. This is actually found out just a few weeks ago, even before our presentation, that this is actually equivalent to a Strauss-Key theorem, which is a theorem, bounding the eigenvalues of a matrix transformed by convergence transformation. It is not very straightforward, but you can show this equivalence. I just mentioned it because it's quite reassuring that you end up with the same bounds using two very different approaches. Now, the interesting part of these bounds is that it tells us immediately that if we choose m hat, this approximation, to be an excellent preconditioner for m, then the eigenvalue ratios are guaranteed to be nicely centered around 1, because the lower bound and upper bound are close to 1. So, if you want to understand mass lumping, probably some information can be deduced by just looking at how good is the lumped mass matrix of a preconditioner for the mass matrix. And the definition I'll be using here is the one of row sum mass lumping, because actually the only definition that straightforwardly applies to isogeometric analysis. The two other ones are very specific to classical FEM, and you can have somewhat generalized into isogeometric analysis. The only one which can be used straightforwardly is this one, because it's just algebraic actually. Note that it's the same definition, but I've included these absolute values because this leads to very general results, but actually the matrices we're applying these bounds to are mass matrix, as I've said, is non-negative. So actually, for the problems we're considering here, we don't need these absolute values. All right, so how good is the precondition spectra? You can prove that the precondition spectra, if you choose this lumped mass matrix, is contained between 0 and 1. In particular, if the matrix is non-negative, as it is the case for the mass matrix here, the largest eigenvalue is exactly equal to 1. So what this means is that this upper bound here is exactly equal to 1. So the perturbed eigenvalues are smaller or equal to the unperturbed guys. And we immediately get this lower bound here, and this implies stability actually. This means that in particular the largest guy is smaller or equal to the one with the unperturbed problem. So straightforwardly we have true stability. Now we can also prove an upper bound here using quite similar arguments. It's not useful in practice. I just mentioned it because I find it quite elegant that if you give a matrix pencil AB, if you lump B, you get an underestimate. If you lump A instead, you get an overestimate. Now, this is good for stability, but what about accuracy? This lemma doesn't tell us anything about it. It just states that the smallest eigenvalue is positive, which you already know actually. And unfortunately, without getting too much into the details, you can also show that the ratio of smallest eigenvalues is unfortunately driven down to 0 as you p-refine. So what this means is that the row sum lumped mass matrix is certainly not something you want to use for higher discretizations, because you're messing up with the low frequency part, and then you're messing up with the solution, definitely. So how can we remedy this problem? We'll be seeing that in a second. Just let me illustrate this with some experiments. So I'll be considering a 2D Laplace on a very classical problem on a stretch curve domain. So it's just for technical issues, you want to break the nice structure of your problem. And I'll be using, on the one hand, for m hat, the lumped mass preconditioner, which you've seen before, and on the other hand, the optimal preconditioner that was developed by Galerkin. So I've heard that he's somewhere here in the room. Great, well, I'm using your preconditioner. It works nicely, I must say. Good job. Yeah, as you can see here on the right is the one for the preconditioner of Lodi. There's also some Gali here among the authors. And you see that the eigenvalue ratios are nicely centered around 1, and between the lower and upper bounds, now as predicted by theory. So, on the other hand, if you use the lumped mass preconditioner, you get a quite different behavior, across the spectrum. You get that the low frequency part is well approximated, as I stated before. Heuristically, this tends to be the case with mass lumping, but actually we still don't have a grip on this. We still don't know exactly why this is happening. It's still something we're looking into, because these bounds are not telling us this. We just get uniform bounds for all eigenvalue numbers k, and that's all we have. So we get a good approximation on the low frequency part, and then a pretty gross underestimate on the high frequency part, which is actually quite advantageous because this guarantees an improved stability, improved CFF condition. Now, okay, we've seen something good, something bad. How can we actually improve upon the bad part and keep the good part? The good part is this upper bound equal to 1, which gives us stability. The bad part is this lower bound, which goes to 0 exponentially fast. So can we improve upon this part while keeping this one equal to 1? I believe the answer is yes, and it's hidden in this theorem. This theorem is based on a matrix splitting operation. So what you're doing is that you're given a matrix A as PD as usual, and you split it between DI and RI. Now DI consists of all super and subdiagonals strictly smaller than I. So I have a picture here below. This is for a matrix of bandwidth 5, and I'm choosing I is equal to 3. So I'm actually constructing a matrix DI here, which has bandwidth 2, and Ri is the remainder. All the diagonals you haven't considered in DI. And to build your preconditioner, you'll be taking DI and then applying the lumping operator on Ri. This will return your diagonal matrix, and as you sum the two, of course, this does not change the sparsity pattern of DI. And this is good because DI is something we can solve for relatively cheaply. Now what you can prove for this preconditioner, Pi, is that the precondition spectra is included between 0 and 1, the exact same property we had for the lumped mass matrix. That obviously, also this is a finite sequence note of preconditioners. For I is equal to 1, we recover the original lumped mass matrix. For I is equal to n, we recover the original matrix A because we just include all diagonals. So in this case, obviously, eigenvalues are equal to 1, and there's a convergence property, meaning that the eigenvalues of the precondition spectrum converge, actually increase for increasing values of I, and since they're upper bounded by 1, actually the entire precondition spectrum converges monotonically to 1 for increasing values of I, and in particular, if the matrix is non-negative, the largest eigenvalue is exactly equal to 1 for all preconditions Pi. So it might seem far abstract. How could that be useful? Well, there's a small corollary of this theorem, which is actually the most practical relevant part, stating that the approximate eigenvalues KPI converge monotonically from below to the eigenvalues of Kn. And I have a plot here for a simple 1D problem with phi noise p is equal to 3 and p is equal to 5. You said the blue curve is for a classical lumped mass matrix, and the red one is for P2, the precondition P2. P2 is tridiagonal, P5 is pentadiagonal, and so forth. You always add a diagonal on both sides. And you see that for the green curve, it actually almost overlaps with the black one. This is why you don't see the black one. Whereas P3 does not exactly reproduce M at this stage. And the picture for P is equal to 5 is quite similar. And this is closely connected to convergence of the precondition spectrum. So you see that for P is equal to 3 and P is equal to 5, you're nicely converging to 1 here. All right, now what I haven't mentioned, but I will mention it here, is that you can actually generalize this construction to even more complex structures. Because I don't know if you're aware, but for isogeometric analysis, if you're using a simple geometry, a square or rectangle or something like this, and separable material coefficients, your mass matrix actually has a Kronecker, is actually expressed as a Kronecker product because you're using tensor product basis functions. And this Kronecker product is quite advantageous because then you can actually build preconditioners, Pij, that are just taken by taking the Kronecker product of the univariate guys. And you can actually prove identical properties for this approximation. So you can, of course, generalize this to higher dimension, but just consider a Kronecker product of 3 matrices and so forth for d-dimensional problems. What also has to be highlighted is that this is quite restrictive because in general you do not have this Kronecker product structure. Unfortunately, if you're using NURBS, which distort the separability of the integrand, if you're using a complex geometry or non-separable material coefficient, this destroys this Kronecker product property. So the idea here is to actually first to do a two-level approximation, or first approximate the mass matrix by a Kronecker product, and there exist some various algorithms out there tailored to problems in IGA, algebraic analysis, or even more black box algorithm developed by the linear algebra community. And once you get this approximation, then you can apply the result I've just stated here above to this approximation. What I also haven't said is that you can actually combine mass lumping also with outlier removal techniques, because as you've seen in these previous plots, you have convergence on the entire spectrum, including the outliers. You are converging the outliers. And this is really a shame, because actually our purpose was to improve the stability, whereas here we're reducing it actually, because we're approximating the outliers. So the idea here is to first then apply outlier removal techniques, which have been developed completely independently. But the good part is that all they do is that they transform generalized coefficient matrices, and A and B, to transform matrices. But those are stored SPD, so you can actually apply these results to the transformed matrices, and the picture you get is essentially the same as I've shown without the outliers, which is quite interesting in practice. Right now, I'm also moving now to understand masking techniques. Now, this is something we use in the engineering community. There's essentially no mathematical theory whatsoever out there. So I want to remedy this. I want to improve upon this. And probably a general way to address both mass lumping and masking is to consider rank K perturbations of the coefficient matrices, because this really tackles actually both problems. And as given as much results for the rank 1 case. Right, well, we've reached the end. Thank you very much for the attention, and I'll be happy to answer any questions.
Okay, is there any question from the audience? Lolly, don't be shy. Okay. So then I have a couple of questions.
Yes, sure.
First of all, there is something I think I missed in your conclusion. So you said that you want to use an outlier removal technique.
Yes.
But you're going to use this on the mass matrix.
Actually, no, it transforms both matrices. So right here, so originally you had the problem Kx is equal to lambda mx. Now this is for the general as you initially start. Now outlier removal techniques, what they do is that they transform these matrices to matrices that have this kind of structure. So it's and M is transformed to this. So you see, just apply H and H transform on both sides. This is actually this has dimensions. This has a size smaller than the original K and the original M. But these matrices are still SPD.
Yeah, but if this doesn't tell you that they will solve the same exact problem as before.
No, no, absolutely not.
So then how do you know that you're still approximating the correct physical behavior? You obtain something that is SPD, but how do you know that you're still approximating the correct physical behavior?
Because these techniques have been just applied to these matrices, and they provably you get the same approximation for the low so the parts for the part without the outliers. And
yeah,
the only thing,
the spectrum, right?
Yes, the spectrum.
But then what happens to the discretization? So this has got a meaning, right? It's the discretization of some differential operator. What tells you that this discretizes the same differential operator?
It is the same, and these are I'm just showing you the matrix part here, but actually there's a whole algebraic part, and the functional analysis part, which
proves that this.
Yes, and I can send you the reference if you're interested.
Thank you very much. I was just curious,
Yes.
because if you substitute the matrix with something that has got a good spectral problem, you might end up with something that
Of course, yes.
Another question. So, since you mentioned Hughes quite some times, considering the fact that you do IGA, he worked on Newmark beta method, which
yes, the method actually, the sample difference method is a particular case of Newmark.
So you put alpha equal to 0 and you put beta equal to 0.5. But did you explore also what happens with the more general explicit version? So alpha keeps being 0.5, but the damping coefficient, the beta in the Newmark beta methods changes.
I haven't explored this any so far, because I'm mostly considering more the theoretical part right now, the outliers, with the eigenvalues and so forth. But this is definitely something we'll be doing in the future, and testing a whole variety actually of time-stepping schemes, and see in the end what performs best. Yeah, so I haven't got an answer yet.
Thank you very much.
You're welcome.
Okay, is there any other question from the audience this time? Okay, if not, we thank again